So last time we discussed about some multiplicative functions. So here is the theorem related to that topic, that if f is multiplicative function, you can say that, and capital F is defined by d divides n like this, then we have capital F is also multiplicative. So we have to prove this theorem, that if f is some multiplicative function and capital F is defined by this, then capital F is also multiplicative. So for this I am taking the help of some lemma to prove this theorem. So the lemma here is, which I am following, that if GCD of Mn is 1, then the set of positive, you can say that, divisors of Mn consists of all products d1, d2, where d1 divides m and d2 divides m, and the GCD of d1, d2 is also equals to 1, and also these products are, you can say that, distinct. So this is the lemma here. By using this lemma I am going to prove this result. And according to lemma, that is, if the GCD of two numbers m and n are 1, then the set of the positive divisors of Mn consist of all the product d1, d2, where d1 is like that divides m and d2 is like that divides also m, and the GCD of these two numbers, these two divisors, are 1, and these are also these product, basically d1, d2, are also distinct. So we are going to prove it first. So as we have given that GCD of Mn is 1, so that means d divides Mn. If the GCD of two number is 1, then that means d divides Mn. And here we have m like p1, k1, p2, k2, up to so on, pr, kr, and n is like q1, you can say j1, q2, j2, up to so on, qs, and you can say that js. So this is the numbers m and q are like that. I can write it in the prime prime decomposition of the product of prime decomposition of number, the product of prime numbers. So that means if I take the product mn, so that is equals to p1, k1, p2, k2, up to so on, pr, kr, q1, j1, q2, j2, and up to so on, qs, js, like this. And we also know that d is basically divisors, so I can write d like d is also in the form of the divisor p1, a1, p2, a2, up to so on, pr, ar, into q1, b1, q2, b2, up to so on, qs, bs. So this is the divisors and this is the product of numbers mn. So here we have the condition that ai are like this, and b, you can say that bs are like, that is some gl, you can say that, like this. And here the number is I is from this, and here the number is L, that is in between 1 and S, and R, that is in I, that is in between 1 and R. And we also know that D is basically a divisor, a composite number, and I can write it as the product of two divisors. Like if I have 6, the divisor of mn, so I can write 6 in the product of 2 and 3. So that means here d1 is p1a1 up to so on prar, and d2 is q1b1 up to so on qs like this. And here this means that d1 divides m. So this is the true condition that this divides m, and also d2 here divides n, and here the GCD of d1 d2 is equals to 1. So if a number we have, if d divides mn, then that means d divides, or I can say that d1 divides also mn, and d2 divides also this condition. So if we have d divides, if I consider this term, so that means d1 divides m and d2 divides n. So this is, and here these two divisors are distinct because this is, if this is 2 and this is 3, so these are distinct, and these are multiplying here, so these are the product of distinct. So that means any two number, if I take a distinct numbers, so their GCD is always equals to 1. So this is the proof of this lemma. Now using this lemma or this thing, I am going to prove this result. So the proof of the above theorem here is, we have to prove that as we know that fmn, that is equals to fm. We discussed earlier this result where we have the condition that mn is equals to 1. The GCD of mn is equals to 1. So we have general result that fn is basically d divides n and f of d, the given statement. So using this result, I can write this term like f mn, that is equals to summation d divides, now here is mn and f of d, here is mn, here is fm. So using this result, I can write this term like this. So, and from the above lemma, I can say that summation, in the place of d, I write d1 d2 that divides mn and f of d1 d2. Now here separately I am taking summation over these functions, so I can write it separately like summation d1 divides m and summation d2 divides n, f of d1 and f of d2. If here we have f is multiplicative, that is the given condition, and d1 d2 GCD of d1 d2 is 1 like here. So that means I can write it as summation d1 divides m f of d1 and summation d2 divides n f of d2. So by the definition, this result is equals to capital F of m, and this result is equals to capital F of n. So that means f of mn here is f of m into f of n. This is basically the multiplicative function, the definition of the multiplicative function. So here I prove that f is a multiplicative function because small f is here multiplicative. So I prove that capital F is also a, you can say, is also a multiplicative function here. So this is the you can say the proof of this theorem. Now here I have some corollary. Corollary that if I have capital F of n summation d divides n f of t, where f is multiplicative, then capital F is also multiplicative, then we have these two results, that tau of n is equals to summation if t divides n is equals to 1, and second one is sigma of n is equals to summation d divides n d. So this is the corollary of this theorem. So the proof here is like f of n is 1, so that means here this is the function that f of n is 1, then fn that is equals to tau of n, because if I take that value f of n is 1, because we have the result here that f of n is basically summation d divides n f of d. So if we have small, I am taking this n, so if this result or this function is 1, so that means we have fn that is sigma d divides n into 1. So this is basically the definition of the tau of n. So that means we have, according to, you can say that according to this condition, I can write it as tau of n is basically equals to summation d divides n into 1. And also tau here, if 1 is multiplicative here, so tau is also multiplicative here. And further is, if f of n is n, there are some numbers, then capital F of n is equals to sigma of n, because sigma of n is equals to summation d divides n d. So if d is multiplicative, then sigma is also multiplicative. So that means we have this corollary that tau and sigma are also multiplicative, or I can write it in the form of tau of n that is equals to summation d divides n 1 and sigma of n that is equals to summation d divides n into d.